Good evening. Thank you. Thank you. My name is Arun Gupta. I work for Amazon Web Services. My first time in Israel, and I've been to like about 40 plus countries around the world. So I'm very excited to be speaking to the Tel Aviv Java user group. So thank you for the leadership for organizing the meetup. Today we'll talk about serverless architecture, best practices, and design patterns. There are multiple ways you can connect with me, either on GitHub or on Twitter or send me an email. The slides are available publicly as well. I can send a tweet pointer where the slides are available. There is a recording of this that is already available, so you can take a look at it, but I guess the session is getting recorded here as well. So you will have your own custom recording. So what I intend to cover in the next 40, 45 minutes, 50 minutes or so is different topics. Talk sort of generally about what Lambda serverless concept is. Then dig into the design patterns that we are seeing with our customers. Talk about deployment pipelines and all those things that we are seeing with our customers in general sense. Okay. So now with serverless, the thing is that there are as many customers and as many design patterns. People are using serverless in all possible ways, Lambda in all possible ways. These are only some of the ways by which we are seeing it being implemented with our customers. So some of the use cases. Let's get going. Let's take a look at what are the key concepts of what define serverless. Now, if you look at this, AWS has this concept of a region, which is a geographical data center in one part of the world. And in that world, or part of the world, there are a cluster of data centers. Each cluster is called as an availability zone. So serverless really means your application is highly available and fault tolerance is built in. What that means is your application is typically deployed across 3 availability zones. So in case something goes down, one of the regions goes down, or one of the zones go down, it'll fall back to the second one. So that's one of the core concept of what a serverless means. That you are not managing the application. The application is highly available, fault tolerant, built in. You don't worry about how those servers need to be managed, which region they are, of course the region you care about, but how many availability zones, what are the right AWS best practices, none of that is what you care about at all. We also look at essentially, today you may be using 10 functions, maybe 10 concurrent users, but if your app instantly becomes popular, you don't have to spin up new EC2 instances, set up CloudWatch metrics, set up auto scaling group, none of that. Your app becomes popular, you get more concurrent users, your app just runs, it automatically scales. There is nothing that you need to do per se for app to scale. And last but not the least, you are not paying for the storage of the function. You're only paying for the compute. So in case of Lambda, for example, you build your function, there is a jar file, the jar file goes up into S3, so you don't pay anything for the S3, but the only time you pay is when your function is being executed. So you never pay for the idle time of the function. Now, if you look at sort of a spectrum of AWS offerings across compute, so to say, you take a look at EC2. You can fire up an EC2 instance. On that, you can set up whatever you want, Kafka, Cassandra, whatever comes to your flavor, you can set it up. You pick a region, you pick how many availability zones, you are responsible for managing it, you run your own monitoring, debugging, logging, all of that is on your own. So you can certainly do that, and a lot of our customers do that actually today. Then second comes is, that is not my core competency, I don't want to get into that business. I just want to have Elasticsearch up and running for me. I want some real-time analytics running for me. So I'm not going to get into that business. Instead, I'm going to just say, oh, by the way, give me an Elasticsearch. It's a managed service. It's available in a particular region. And you just say, okay, make it highly available, and that's it. So AWS will take care of making it highly available for you. And similarly, you can take a look at RDS. Offer a variety of databases, essentially, that you can take a look at it. Anywhere from Aurora to Postgres to MySQL, whatever you want. Those are all could be made highly available. And then on the last far right, what you see is sort of the serverless landscape, essentially. These services are, you say, I just want a Kinesis stream because I want to do real-time analytics. You pick a region, And that's it. You said, spin up a Kinesis stream for me, which is by default highly available for you. We take care of managing the Kinesis instance in the background. You get a multi-tenant control plane and all those good things. And you want a DynamoDB? Sure, give me a DynamoDB, and we take care of scaling it, auto-scaling it, and all those things for you. You don't have to worry about it. You ask for a resource, and the resource is available to you. That's sort of, and the concept of serverless, essentially, as we talk about it. Now, if you look at it, how Lambda was started, if you go back, what was the first service that AWS launched?
S2.
S3. S3 was the very first service that we launched, actually. And if you think about the concept of S3 is, I want a storage, and I don't want to manage the storage. Literally, I think second or third day S3 was launched, Andy Jassy, which was a much smaller company at that time, got an email that, oh, you know what? Somebody want to buy 6 terabytes of S3, second day launch of the product. And so if you think about it, AWS has actually grown organically that way only. And they're buying 6 terabytes of storage because they don't have to manage, because they're not in the storage business. So S3, if you think about it, we have been doing serverless pretty much since day one. This new term has been coined recently only. So the way Lambda was introduced is, our customers were asking that, hey, we need some compute capability when something is stored in S3 or something occurs in S3. And that's how exactly Lambda was identified. Now, 90 to 95% of our roadmap is driven by customers, because customers ask us those features and we go from that. And that's what led to the genesis of AWS Lambda. That, okay, we're going to give you a compute capability, some object is stored in S3, and let me actually give you a compute capability, and that's AWS Lambda. So let's take a look at it. How does AWS Lambda work? What are sort of the key concepts over there? So first of all, 5 different languages supported, Java, Node, Python, C#, and now recently Go as well. In those specific languages, you can prepare your binaries, upload them on S3, and you can set up your triggers. We'll talk about triggers a little bit later, but essentially, if something happens in a particular Amazon service, do this for me, or invoke this Lambda function for me. And people have been running their own runtime. Some of our customers are actually running Fortran, because Lambda has the capability of bringing your own language runtime. So that capability is there. You also think about how Lambda gives you a one power button. It's like you want to turn the fan on, you just rotate the power button and the power increases. That's about it. So it's as simple as that. So we don't give you a choice of, oh, you want CPU and memory and network and all those things. We'll just talk about, okay, there's one power button in different increments. You pick that power button, and then we give you, your CPU accordingly. You just give me the memory requirement, and we allocate CPU and network accordingly. And I'll talk about that a little bit later in the slide, where it becomes more clear on how that acts as a power button. There are different programming models. There is synchronous, asynchronous, and streaming model. I'll talk about that a little bit later as well. And it's fully integrated with, not only just AWS services, but particularly with IAM. How you can start assigning IAM roles, that this Lambda is going to execute in such and such IAM role. What capabilities does it have? What services can it invoke? So if I now look at sort of my Lambda execution model on how, what are the 3 different ways typically users use it. So the first one is push model. So you have a Lambda function sitting up in your S3, and you have your AWS Lambda configured that, okay, this is the function and this is what needs to be executed. You can do that via console, programmatically, multiple ways. But end of the day, your function is sitting in S3. That's where your jar is, because that's what gets downloaded and expanded and run. So Lambda function by itself, you cannot invoke. So what you would do is you would typically front-end it with the API gateway. And you say, this is my REST API. Whenever this REST API gets invoked, that is my trigger, call this Lambda function. And you can easily configure that. So that's sort of my first model, which is a synchronous push model. So I'm making a call, I'm getting a response back. It's a synchronous request and response. So the client is blocked until you get a response back. The second one is asynchronous, which is more event-based, where the code is sitting somewhere in S3. SNS or a SQS queue. Somebody sends a notification to the SNS, or somebody sends a message to the queue. As soon as that event occurs, it just automatically triggers the Lambda function. There is no client blocked that, okay, I'm going to get a response back. A message has been sent to the SQS. Maybe what you want to do is, as soon as the message is received, look at the message, introspect the message, and alert something or somebody. So that something like that. So that's very asynchronous because you're not really blocked upon it. And the last one is basically stream-based, where you are looking at essentially either a Amazon DynamoDB or Kinesis, which is a real-time streaming service or analytic service, where you can say, as the objects are stored in DynamoDB one by one, keep calling this Lambda function. Or Kinesis, where as you have multiple shards, we'll talk about that later, but as you have multiple shards, as you are receiving events, for each event, invoke this Lambda function. That's more like a streaming operation. So in each of these, essentially you do have a AWS Lambda function that is being invoked for you. What does the Lambda function look like? So, well, this is Java user group, and I particularly use Java for all my Lambda functions. So it looks pretty simple, actually. At the very top, what is not shown over here is you have to implement an interface, which is available to you as part of the AWS Java SDK, which is, by the way, 100% open source. So you implement that interface. As part of that interface, you get a method. You have to implement that method. In this case, that is handle request from that interface. So the name, of course, is there. Now, the first parameter of that method is the payload, because when you're invoking a Lambda function, you are sending some payload to it. In this case, I just want to save a book. Somebody is making a request from my web page, that goes to the API gateway, that goes to the Lambda function. So you're giving me a book data, and yes, I've converted it to JSON or POJO, and in this case, I'm taking the POJO and I'm writing the book to my database. Save book is my method essentially, which is actually doing my persistence mechanism. Then context is the runtime of the Lambda function, which gives me context ID, request ID, and some other details around the Lambda runtime itself. What Java version, where is it coming from, things like that. So you can make some more sense out of it. And in case you want to act upon it, you can act upon it. Yeah, so those are sort of the three things. And then the handle request method particularly is called as a handler. The core concept of Lambda, if you look at it, is very simple, very small, okay? But then you build upon that. So there are certain known best practices, particularly when you are building not just Java, but any language in that sake. So let's take a look at it. All my examples are certainly from the Java language. So now I have my book post handler here, and as I said, this is my interface that I need to implement. So this is my request handler interface. And I'm defining it that, okay, book is a payload, string is a return type in this case, and I implement the methods handle request, and I'm doing everything in my method. I have my save book method kind of chucked out separately, and there's a reason for that. Let's take a look at it. First thing is, I am doing my initialization as a DynamoDB mapper, which is sort of my DynamoDB class, on how I'm going to do interaction with DynamoDB. I'm doing that as a static initializer. The important part for that is because this is JVM, it needs to warm up, but once it warms up, then it's pretty rock solid and works very well. So in Lambda functions, you can have up to 1,000 concurrent connections or 1,000 concurrent executions of it. So if you can have 1,000 concurrent executions, it's the same runtime that is being used. So now imagine 1,000 concurrent executions of this handler happening, and you have to make 1,000 connections to the database. But the fact it is a static initializer, that we just repurpose that connection.
When you're saying 1,000 concurrent executions of Lambda function, do you mean 1,000 containers, or it's 1,000 threads?
I don't think we need to think about threads or containers, because for each, this is going to be you spinning up a separate instance of the function for you behind the scenes. Mm-hmm. So it's not really a thread per se. And that's why the static initializer kind of give you the DynamoDB database mapper, which is shared across multiple classes of that. The other important part of it, I'm also separating my Lambda handler from the core logic. And the advantage of that is this also increases the testability of my function. Because now, if I were to test this Lambda function, I can just say, okay, I can put a public static void main class, and I can invoke the save book method directly itself. So I can start improving the testability of it. Otherwise, every time I have to go through API gateway and test the method that way. But now I can write a unit test, which can actually call the method. And the database util method, the mapper can automatically is called from the save book method. So the two concepts being static initializer and improved testability.
Excuse me?
Yeah.
Yeah, about what you said before. What happened? You said that it's the same JVM for all this up to 1,000 calls. What if it's another language like Python or Go? What happens then? Is it still the same?
It is very much exactly the same concept. So these concepts, what I'm showing you is for Java, but they apply across the languages. So there's still the whole, if you do the static initializer, if there is a similar concept in that language, they're still being shared accordingly. Now, let's take a look at the packaging part of it. Now, I'm using AWS Java SDK. So I could simply say, okay, import my AWS, not in this case, but I could just say import my AWS Java SDK Maven coordinate. Now, with Maven or with Lambda, you are uploading a jar file to S3. And there is a limit to the size of the jar file, which cannot exceed 50 megabytes. But if you import the entire Java SDK, that jar becomes big, and then your application code and everything certainly explodes far, far above. So the recommendation here is Java SDK in general is broken down into multiple modules. So let's say in this case you are using only the DynamoDB. So just import the Lambda Java core and DynamoDB core. So just importing those two particular artifacts, in which case your jar file kind of stays much smaller, but you still have all the right pieces as part of your fat jar. Now, some of these artifacts are also available in the Lambda runtime, but the idea is we want you to package the exact dependencies as part of your fat jar, because we don't want your application to break if we change the runtime in the Lambda itself. So it's important part to create a fat jar and the exact version that you care about. Another important design pattern is how we highly recommend to use environment variables. Several advantages of using environment variables. First of all, if you're storing in a S3 bucket, you don't want to hard code the S3 bucket. It's a very usual programming practice. So you can use an environment variable. Second is, EC2 metadata API provides you certain default environment variables. Those environment variables are actually exposed to your Lambda function. So AWS region being one of those. So in case you want to act your method differently depending upon the region, you should use that. The other one also that you want to think about is that you can, all the environment variables that you are using or you are setting, they're actually encrypted, during the storage time of it. So they're not accessible otherwise. So they're encrypted on the storage, and when they're accessed, at that point they're decrypted. So the advantage is that you're using environment variables, keeping your code configurable. Depending upon the region, you can choose the right bucket or whatever you want to do, but be assured that the environment variables are absolutely secure from your perspective.
I remember I use environment variable of the Lambda itself.
Say again?
In the Lambda code, I have option to put the environment variable outside and then pass it to the code when it's running.
Correct. There are multiple ways you can do that. Because when you're running the code, only in the console you have access to it. But my point is, when it's actually running, when somebody else is accessing it, they don't have access to that environment variable at all. On the disk, when it is stored, it is in the console. Yes, you will be able to see it. But when it is persisted on the disk, by any chance, if somebody have access to your code, they won't be able to see what's really happening, the value of the environment variable.
Even on the GUI, it's not encrypted there, when it's shown there?
No, in the GUI, you can actually see the variable.
It's not encrypted.
It is not in the GUI itself, but when it is when it is stored, then it is encrypted. But when it is accessed back and you want the value, then at that time it is decrypted. Now we kind of touched upon this point a little bit earlier also. You want to make sure you use a Maven Shade plugin to create a fat jar such that in case Lambda runtime dependency changed, in the background, we don't want your application to break because we could update a particular version of Java SDK or the Java runtime. So if you're saying Java 8, then we'll give you a Java 8 compliant runtime, but a particular version of the library, don't rely on it being in the Lambda runtime itself. Now we talked about the big power button. So let's take a look at that for a second. Now, this is an example that shows how can you generate, how much time and cost it takes to generate 1,000 prime numbers less than a million. All prime numbers less than a million, 1,000 times. And it's just running that again and again and again. And the same method was executed with 128 megabyte, 256 megabyte, half a gigabyte, and 1 gigabyte memory. And how these results were generated are captured on this GitHub URL. This was done by somebody in the community. But now if you look at the results, the result is exactly the same, because what you're getting is all prime numbers less than a million and 1,000 times. But if you look at, if you were given 128, the compute time is almost 12 seconds. Cost is about 0.024. But if you look at 1 gigabyte, compute time is cut down to almost like 10%, and the cost is exactly the same. So the point that you want to think about is, make sure you memory opt, because memory is sort of the big power button. If you allocate more memory, we give you more CPU as well. And this is a more CPU intensive function. So just by allocating more memory, you are actually incurring exactly the same cost, or pretty much the same cost, and getting the execution much faster. So make sure you optimize for it. Put the right memory type accordingly, and see if your function is CPU intensive, network intensive, what it is, because then accordingly the power dial works for you.
The question: there is no downside to allocating a lot of memory. Why not just put 1,000 megabytes every time?
Ideally, no. I mean, if this is your function, if this is more CPU intensive, yeah, absolutely. And this is an experiment to really show that, because people generally think that, it's gonna charge me more, but the cost is exactly the same here. And then, as a matter of fact, if you go up to until like first 4 decimal digits, the cost is pretty much the same. So in that sense, yes, and that's what I'm saying, that because more memory means more CPU to you. But if your function is, say, it needs less memory and it needs less CPU, then there is no point, incurring that cost as well.
Do you have any comparison between writing a Lambda function and running it versus running it as a microservice inside a container?
It's a very hypothetical question, actually.
But let's say a rule of thumb: when would you use Lambda, or when you would prefer to have your own container?
It's a very theoretical question, I think. But I know that is something that a lot of our customers struggle with. How about we take that after because we can talk about it endlessly, okay? But do remind me of that question, though. I have my opinions on that. You also need to be aware of some of the limits on Lambda. So for example, the total number of functions that you can store in a region is 75 gigabytes. So we have our customers who load a lot of functions up there, in the region, and then they say, I don't have any more storage space. But that is limited to 75 gigabytes. And that's a lot of functions essentially with 75 gigabytes. So make sure you delete any large unused function. There are limits like the jar file size is 50 MB. The expanded jar file could be 250 megabytes. And there are more limits over here. For example, how the memory allocation range works. To your question again, a Lambda cannot execute for more than 300 seconds. So you stop right there itself. If you are running a microservice, which is a persistent, like you're running a Tomcat server over there, which is continuously accepting requests, it's a more event-driven architecture as opposed to a long-running architecture. That, my Tomcat server is sitting here and it's accepting requests. You probably have like a API gateway sitting in front of it, and then building your application maybe using Elastic Beanstalk or ECS or Kubernetes, which is then calling this API gateway to do a particular thing. So that's sort of the architecture you want to think about in general sense. So one of the common questions that people ask is, how can I, so I understand the Lambda concept that, okay, I have a function, but how do I do my local development, deployment, debugging, testing of that? And more importantly, how do I do the deployment to Lambda? How do I make it simple? That's where we introduce the concept of SAM, or Serverless Application Model. Now, Serverless Application Model is a DSL built on top of CloudFormation, and all it is it provides a YAML file. It is basically a CloudFormation script only, but with a particular transformation that can be applied to it. And essentially, it introduces new serverless resource types for you. One for the function itself, then for the API, and then for a simple table. And what you can do is, in a simple YAML file, you specify those resources, you specify the transform, single line essentially, and then your function, your API gateway, and your DynamoDB database table, they're all created for you. And I'll show you how that entire development cycle look like. The advantage of that is, if I'm a Java developer, I have a Maven file. In the POM XML, I say generate my jar file. In my SAM template, I can point to the local jar file. I can continue testing it locally using SAM, because essentially what it does, it basically downloads, it mimics the Lambda runtime using a Docker image on your machine. You can keep testing it. Your resources that the Lambda function is accessing are still sitting in the cloud, like DynamoDB database table that could still be sitting in the cloud. But your Lambda function, then you can iterate upon that much faster. So that's the ability it gives you. And then let's say if you need other resources in addition to just function API and DynamoDB database, you can put them in the same DSL itself. So you have one template SAM, and using that you can do your entire local testing of the function itself. And then when you're ready, then you can say, now go upload this and create my resources. So let's take a look at how my SAM template really looks like. So this is what my SAM template looks like. On the very first line, what you can see is what my AWS template format version is. That's a standard CloudFormation version. I apply my transform. This is a single line, essentially telling that, okay, apply this transformation to the DSL language, which will automatically take this DSL and generate the corresponding CloudFormation for you. Now I'm saying, all right, I have a get function right above this arrow essentially. So that's going to be my function name. And then this is a serverless function. I specify my code URI, and you can see this is really pointing to my local jar file, whatever that jar file is. So I continue to iterate upon that. Before that, I'm of course saying my runtime is Java 8 and my handler, which is from that jar file itself. From that, I can refer to environment variables. And in this case, for example, this is a book handler that I've created. So I'm referring to a table name environment variable in this case. And I'm just referring to a table which is created down below. And in this case, it's a simple table, which is a new resource that we've introduced for the SAM. Or it could have referred to, for that sake, a full-blown DynamoDB database as well. Because this is an actual fully functional CloudFormation script, essentially. And the table name is the environment variable that I could use in my code. So I don't need to worry about what the exact table name is going to be. This will be generated by the CloudFormation script, but I'm concerned about the table_name environment variable. And then finally, what I do is I specify how my API is going to look like. In this case, I'm saying, all right, you put a function, you put a DynamoDB database table behind the scene, front-ended with the API gateway as well. And I'm saying HTTP GET, and here is my path /books. So imagine if you take this SAM template and you deploy this SAM template to AWS Cloud, the function is automatically uploaded in the S3 bucket for you. AWS Lambda function is created for using that S3 bucket. API gateway is created for you. A DynamoDB database table is created for you. And how does that deployment cycle look like essentially? Well, to begin with, I just use SAM package. And what does it do? It'll create a deployment package for me. Based upon all the information that you have given me, it'll take the jar file, that's a fat jar file already. It uploads the deployment package to an S3 bucket so that it's ready. So the package is ready now. So you can keep testing once you have done the package part of it, because the code is already uploaded. So your Lambda function is not created yet, but the moment you say SAM deploy, at that time your resources are created. So whatever your API gateway, whatever needs to be done, those are created for you automatically. So you can keep testing locally using SAM package command, and then you can also fire up your API gateway and everything around with that. There is even a local version of API gateway as part of SAM, so you can continue using that. And once you have done enough testing, then you can say, now go ahead and create my resources. Now, SAM local is basically what I was talking about. This is a CLI for local testing of your serverless applications. It works with Lambda functions, of course. That's what the whole intent is. The reason you want to test your function locally is because all your logs are now local to your machine. The function logs all on your local machine, so it's a lot easier debugging essentially. And there is integration with popular IDEs as well. For now, it is actually supporting Java, Node.js, and Python. Those are the 3 languages, at least from SAM local perspective, that we support. And this project particularly is done fully in the open source. I was talking to somebody how open source landscape at Amazon is changing. This is something that our team was very successful in driving. That we were working with the serverless team very closely, and this is done fully in the open source. And we are not only accepting requests, but we are also requesting issues or in any way you want to contribute to this. One of the questions people ask is, I understood the basic development model, but when I go into production, I don't use CLI, or I don't push the code to production by hand. I want some sort of a deployment pipeline to take care of that. So let me explain how that works for us. This is how Amazon.com used to look about 4 years back. This is sort of Amazon.com architecture essentially. Thank you. What these are is essentially, it's built, Amazon.com is built as a set of microservices. And you can see all of these microservices that are making Amazon.com work right on the top. Each microservice is a single purpose microservice. It does one single thing. They're all connected only through APIs. There are no hidden contracts or private APIs. They just talk through, very, very publicly published interfaces between them. They only connect through HTTPS. The services themselves are largely black box to each other, that they don't know what are the implementation details. Here is a contract, and here is what's going to be honored. Here is the inbound and the outbound payload, and that's what is going to work for them. Microservices is the term. Now, in 2014, to make Amazon.com work, we were doing about 50 million deployments a year. What that means is, in about 45 minutes of talk that I'm giving here, in 2014, we would have done about 4,500 deployments in that 45 minutes. And you can only imagine the rate of deployment is only much larger now. This is a problem that our customers also were having. And of course, we weren't doing the deployment of this by hand. All of this was in a very automated way. Amazon is a very numbers-driven company. So once we have numbers for it, that we need to automate it. We are big freaks on automation in that sense. So this process was completely automated, and that's what led to the genesis of AWS code pipeline. Now, that is something I should have done earlier, but I have not. So let's give it a shot. How that code pipeline works, particularly for AWS Lambda. So code pipeline, code commit, and code build are 3 managed services that are provided by AWS. And these are fully managed services where you can easily configure a deployment pipeline. So instead of using Jenkins, for example, you can use this. And the big advantage over here, the way I look at it is fully managed. I don't have to worry about which plugin and what's going to work, what's not going to work, or how my master and slave are going to work with each other. None of that. This is fully managed. It's fully scalable. So if I go to code pipeline here, I can say get started. I won't take too much time here because this is gonna take a while to go through the entire demo and not only create a CloudFormation stack, but essentially this is where you can create your entire pipeline. You point to your GitHub repo or your code commit repo. well, actually at this point of time, it requires you to create a new repo, but a feature that is being worked upon is how it can link to an existing repo as well. So typically what I do is I will say, okay, create me a repo, and then I'll pull it from my existing repo into that repo because it's kind of sensitive about that. But once you have that up and running, then you have your phases very clearly identified, and you can say, okay, after build, do this and this stage, and those are all going to be very graphically and very easily defined. I apologize, I should have created this. I think this is one demo that I missed out creating ahead of time. But if I have time at the end of the talk, then I'll see if I can get it up and running for you guys. Now, once you have application up and running, the normal question is, typically if you look at a Lambda function, it's not just a function by itself. You will have an application with multiple Lambda functions in it, and they're possible in different languages, or maybe even if in the same language, but these are multiple Lambda functions. So how do you really compose them together? And more importantly, how do you monitor them together? So let's take a look at the monitoring aspect of it. Now, once again, at AWS, we have a fully managed service called as AWS X-Ray. And what it does is it allows you to monitor your incoming requests, and it provides a full end-to-end visibility into your application. So essentially what you do is, using your AWS X-Ray SDK, you instrument your code. You start creating segments and subsegments and so on and so forth. And once you have those segments created for you, then it automatically generates the traces for your application, and it allows you to drill down into what your application looks like. So what I'm showing over here is how a simple Node.js application could be easily instrumented. So all you're doing is including the X-Ray SDK, setting the sampling rules, which particular paths need to be sampled, then you capture, and then you say whatever your application business logic is. So let me show this one I have up and running. So let me show this in action. So what I did is I created a simple Node.js application, and that Node.js application is using essentially, if I go here, this is a simple Node.js application. It's simulating requests. As you can see, it has simulated about 515 requests so far. It's sending most of the requests as successful. Some of the requests are unsuccessful. So, and then it kind of start capturing how long it takes to serve a particular request. So if I go back here, if I say, show me the request in last, say, 15 minutes now, if I refresh it, so you can see, it kind of shows me green as okay and error as 10%, because that is intentional error that is being introduced in the application that is meant to fail. Now, if I click on this, my front-end dev, I can see more details about it. It shows me sort of the legend over here. Now I can look at the traces here. If I look at a particular trace request, I can start getting more details. I'm seeing here, for example, this is taking 200 milliseconds, or this is taking actually 71 milliseconds. This is taking 27, this is taking 42 milliseconds. So you can start looking at the traces for each and every of your application. If I go back here, I can look at another request and kind of start looking at it, what's really happening over here. So you can start getting traces for it. Now I can go back, and then I can say, okay, show me what's happening in this SNS application. So because this is again another Lambda function here. So if I click on view traces for it, and now it's showing me what's really happening for that one. If I go back to the service map here, I can start drilling down into the different level of details, show me in last 5 minutes, so you can start seeing the error rates over there. So you can start picking your Lambda functions, and then it'll trace the complete end-to-end request of what's really happening. Not just the Lambda function, but even down to your database essentially, how long it's taking to invoke that request. And so that really gives you a full-blown visibility. One of the sample applications that I've been working on, and literally I was debugging with the team this morning, is how to get this application up and running, a Java application up and running on a Kubernetes cluster, and show end-to-end visibility over there. So that's something I should be tweeting, hopefully blogging in the next few days. Now, as we talked about, one of the primary uses of Lambda is event-driven architecture, because that's what it is well suited for. So how does event-driven architecture look like? So what happens is, you call something, you store an event occurs, an event A occurs, and that event could occur because you are storing something in the S3 bucket, or event A occurs because you store something in a DynamoDB database, or your SNS received a notification, or your SQS received an item in the queue, whatever that event occurs. You could have a series of events occurring. A could trigger, B could trigger C. Eventually, there will be a Lambda function that you may want to invoke, which is actually your business logic. So for example, you could receive something in a SQS, and you can have a Lambda function sitting right there, which will say, take that message, process that message, and if it makes sense, generate an SNS event, which could then trigger a Lambda function. So you could really have a pipeline of those events all working together. Now, if you look at it, there are the Lambda functions can be invoked in response to about 18 different sources. So it is the most comprehensive platform essentially that we have, where you can have all different sort of services, event triggers, and then when your Lambda functions is happening, that Lambda function could then invoke any of the services. So that really gives you the flexibility. Think of Lambda functions as the glue for putting these sources together and be able to interact with each other. Now, not until too far ago, the media companies particularly will be using FFmpeg, which is a tool by which they will take an image, get the EXIF data out of it. So let's say somebody uploads an image. They will use FFmpeg to get the EXIF data out of it. Then they will figure out what is the size of the image, and then they will resize it to multiple formats, and then they'll store it into S3, and then say, okay, now I can resize it, rescale it, whatever it needs to be done. And that's exactly sort of the example that's done over there. So instead of, some of the customers who actually use this deployment model is listed at the bottom, but that was sort of one of the primary uses of Lambda as well. So what happens is, you are driving, you are walking, running, whatever. You see a nice picture, you upload the picture up to say Seattle Times or Washington Post or whatever it is, okay? You upload it, goes through S3 bucket. As soon as it goes through an S3 bucket, event is triggered, Lambda function is called, the Lambda function grabs the image, it resizes into different formats, to different form factors, and it puts it into the destination bucket or a DynamoDB database, wherever it needs to be. So as soon as the image user uploads the image, there is no other magic that needs to perform. You can still continue to use your tools, but instead of manually performing their job, because this is what the Lambda function exact use case is, trigger an event. You upload an image, you trigger an event. Now, I have, if you look at this, I have a S3 source bucket, I have a Lambda function, I have a S3 destination bucket, and possibly, in a more complex use case, I'll have multiple AWS functions or multiple AWS resources working with each other. So how do you compose such an application? How do you create a microservice, so to say, out of these Lambda functions? And that's exactly what your AWS Step Functions are used for. So now you can create an application using your Lambda function. You can say, trigger this AWS Step Function, and which exactly defines the flow of the Lambda function. So in this case, essentially what we're saying is, extract image metadata, check the image type. If it's not supported, then terminate the flow. If it is supported, store the image data, and then you can use, for example, AWS Recognition, which is again a service by AWS, which allows you to, which is a high-level machine learning service, which provides you some data about recognizing what's in the image, what are the characters, what are the attributes, and a lot more functionality. And you can add the tags and store the thumbnail and end the workflow. So let me show you this exact workflow on how that would potentially look like. Well, the architecture is over here essentially. So now I have my step function. On the far left, what I have is my test application. So as soon as I upload an image, the image goes to S3 and it triggers the Lambda function. The Lambda function says, okay, it extracts and validates the image data. It calls another Lambda function, which then talks to Amazon Recognition, which kind of grabs all the information for me. Now, put all the metadata that is required for it. It generates the image thumbnail using another Lambda function. And then finally, it calls one more Lambda function that stores the image into the DynamoDB database. So think of that as an application that is now composed of multiple Lambda functions, and you have exactly defined how the flow is going to look like. And AWS Step Function allows you to do that in a very visual way. So that's sort of the whole advantage of it. So let's take a look at it. So I just did this, for example, a few minutes ago, right before the talk actually. So now what I'm going to do is I'm going to click on Browse. I'm going to pick an image, say for Stephen Curry. I'm from Bay Area, so that's our favorite player. I'm going to pick it up here. So as soon as I click on Upload, that entire step function choreography is trading up. It's uploading the image to S3, then it's gonna call the step function that, okay, the state machine is executing, then it's gonna generate the tags, it's gonna upload the image into DynamoDB database, and now it shows. And once it shows up here, you can see, yes, it is not recognizing as a sports person, but at least it identifies and it puts the tags. And these tags are dynamically generated. So that entire flow of S3 and DynamoDB and recognition and all of that was triggered by just that upload of an image. And that was all choreographed in that step function itself. So it's very intuitive to work with it that way. Let me talk about one more use case here, which is about real-time streaming. How many of you play Clash of Clans? Yeah. I was seeing that statement earlier. It was like 32 billion logs per day, something like that. I may be incorrect on the numbers. Any guesses how many events are generated by Clash of Clans per day? Take a wild guess. How many? 1 trillion? 50 trillion?
A lot.
Well, so let's be realistic about it. 45 billion events per day is what they generate. So all the players who are paying, and this is Supercell is a company behind AWS with Clash of Clans. They generate 45 billion events per day, and those events are all stored in Kinesis, and they're all processed by a Lambda function. So that's sort of what I wanted to highlight over here, how real-time streaming works and how Lambda is a perfect fit, particularly how it blends with Kinesis particularly. So let's talk a little bit about Kinesis. Kinesis allows you to do real-time streaming processing very easily. We introduced Kinesis first in 2013, then 14, 15, and 16. The portfolio has always been constantly growing since then. We have 3 offerings essentially. So there is a Kinesis Streams, Kinesis Firehose, and Kinesis Analytics. So their target markets are a bit different. So if you look at Kinesis Streams, it allows you to collect and stream data for real-time processing. So that's really what we work on streams. Kinesis Firehose, it allows you to load massive volumes of streaming data into S3 and those other, for example, Redshift or Elasticsearch. So that's sort of the next evolution of the stream itself. And Kinesis Analytics particularly allows you to run SQL queries on top of your data that is stored as part of Kinesis. So let's take a look at it, how this architecture looks like, particularly with Kinesis. Think of Kinesis as a freeway. In a freeway, you have, or a motorway, or whatever the terminology is. In a freeway, you have 4 lanes typically. Everybody is running in their own lane. The traffic flows very freely, very fast. In an ideal world, if you want to increase the flow of the traffic, you will create more lanes. Well, that's not possible in freeway, at least, because those are limited by the geographical space. But in Kinesis, essentially, you can have multiple shards. Shards is a lane. So essentially what you do is, when an event occurs, you send the data, that data goes into a shard. So you can have thousands of shards in a Kinesis stream, and then each shard could then have a Lambda function associated with it. And what you're saying is, anytime a data goes through a shard, invoke that Lambda function, and that Lambda function is then going to process it. And how is Supercell really using it? How Clash of Clans is using it? As the players are playing the game, they are constantly monitoring how the players are doing and how they're moving, and they're sending the player movements back to a Kinesis stream. And the data is essentially that, are the players able to manipulate this part of the game? Are they able to move forward in this part of the game? Or is it something that they're finding it too difficult or too hard, so that they can help evolve the game and continue to kind of improve the game going forward? So they collect that real-time data at any given point of time, and then accordingly evolve the game. So as I said, you have multiple shards, and for each shard, you can have a Lambda function very easily associated with it. You can easily connect to a streaming source, and once you have the data with you, you can easily write SQL code on top of it to process the data. Okay. So what I'm going to ask you is, if you have a cell phone, a smartphone, take out. I'm going to show you something here. Yeah, get out your cell phone. Get out your cell phone. I'm going to ask you to scan something. So basically what I've done is I have a simple demo. That demo will show you essentially how Kinesis and Lambda are working in the background here, okay? So for that, I have a dashboard here, okay?
The demo is a bar.
Second, I'll show you the bar. So scan this URL. This will show you a quadrant, okay? It's basically a quadrant with a ball, and you can move the phone up, down, left, right as you move it around. As you move it around, I'm showing the data right here. I'm showing quadrant A, B, C, and D. Depending upon how many of you are in quadrant A, and as you move your thing around, the answers will change, okay? Now, let's for fun's sake, everybody go to quadrant A. Quadrant A. See how the data, is just real time. In about 2 to 3 seconds, and not real time, but almost real time. Now everybody go to quadrant C. And you'll see in about 2 to 3 seconds, the data gets, right away moved up to quadrant C. So it moves, so this is happening in real time. And I'll explain you the architecture behind it. Hang in there on quadrant C for a second. So if we see, the iOS is about 4 phones over here, and Androids are about 11. Well, no Windows phone users here? Nobody uses Windows phone? Something to do with the Windows phone. I have rarely the percentage is either 1 or 0. So with Windows phone consistently around the world though. Although I'm surprised by the number of Android phones over here, very little iPhones here. So anyway, the idea is to show you that how this real-time streaming works very easily. This is setting with a Kinesis background. The analysis is all happening using a Lambda function, and this chart is generated using simple JavaScript. So let me explain the architecture for this one now. So what happens is on the dashboard, or well, actually when you scan the URL, it downloads the JavaScript and all the things that are required for the quadrant to show up on your web page. Okay, that's hosted as a S3 web page. You download the page with the JavaScript libraries and everything. Now we're using Amazon Cognito, which is for mobile developers. You can use authentication, etc. for this, but we're using Amazon Cognito to send a unique ID as part of your trace. We capture the data, where the ball is sitting in which quadrant as the payload, and that payload is essentially sent to an Amazon Kinesis stream. From the Kinesis stream, I'm building my data pipeline. I'm putting Amazon Kinesis analytics over there. Then I'm saying, okay, I want certain kinds of data. Now I'm going to take a look at it, how I need to process the data, and then I pass it on to another Kinesis stream. So I have sort of built my data pipeline right there, with stream to analytics to another Kinesis stream. And finally, I have the Amazon Lambda function, which is sort of applying my business logic, which is sort of saying, okay, filter the data the way I want to and store it into an Amazon DynamoDB database. So this is essentially for storing the data, but this is where your data processing is essentially happening, okay? And then, of course, I'm looking at the dashboard right over here. So as you realize, as you are moving the phone left and right or top and down, that all this processing of the data pipeline, storing into the DynamoDB database, refreshing the page, was happening in about 2 to 3 seconds.
What the screen doing?
Second?
The bucket one is using for what?
That's where the static page is hosted.
Okay.
The JavaScript page that we were talking about, that's where it's hosted. So that's because S3 can be used as a website as well.
Question: the dashboard app is calling the DynamoDB, or?
Yeah, as you see, the data was constantly being pulled from DynamoDB.
Could have you extended this by having change sets from changelog from DynamoDB into Amazon IoT and then using WebSockets into the?
Oh, you can do all kind of fun things with it. Absolutely, yeah, you can do all sorts of fun things with it. Now, what I'm showing you here is also how the SQL query looks like. And just to be honest, we are looking at Android count and iOS count and Windows Phone count. We're not just ruling the Windows phones out already. But you can see sort of what we are looking at it. But this is sort of essentially what kind of gives me certain data, as I'm doing my analytics performances over there. So I can take a look at it, Android, iOS, phone. Then I'm looking at quadrant, and that is coming as a cognitive ID essentially. So from the quadrant A count, and then once I gather that data, I send that data, store it into DynamoDB, and then I get the results, my DynamoDB or my dashboard refreshed. So that's again another classic use of serverless. Now, serverless application repository is something that we announced recently as a GA, and a lot of our customers are building serverless applications using a lot of different ways. So what is serverless application repository? This is where you can actually store your serverless application and showcase it to the real world. So here, for example, I don't have time to understand how this whole thing works. Just get me a working application. So if you go to serverless application repository, you can search and discover simple applications and complex applications that our customers have published over there. You can have that application provision in your environment. You can configure the application, then you can deploy it from there and manage it from there. Now, one of the things to remember is for Lambda functions, first million functions are free per month. So it's very easy to get started with it. So a lot of our customers actually start that way, and then if it grows from there, the pricing is very nominal actually. So I would definitely recommend. It's very easy to get started with it. And if your hobby project is getting more than 1 million requests per month, I think it's a pretty hit hobby project. Then it's about time to maybe start paying up a little bit. Pretty much my last slide here. So I'm going to conclude with some further readings. We got some white papers, we got some architectures that you can take a look at it. I know these are all hard to remember, so I will share the slides. But this is sort of one URL where all the white papers, all the tutorials, everything that we're talking about, serverless or Lambda, is connected from. Any other questions?
What is the price for pipeline management?
I'm not fully familiar with the Kinesis stream pipes particularly, but I would say the pricing should be on the web. So if we can go take a look at it up here, I definitely recommend to look at the service itself. So I will say aws.amazon.com/Kinesis, or what, better, let's do this way, Kinesis pricing. So here you go. So it just brings you right there itself, Kinesis data streams pricing, and that's the very first URL. By the way, one of the things, we started Amazon over 10 years ago, and we have reduced our prices 65 times since then. And we have only reduced prices because one of the things that we fundamentally believe in is that because of the economy, and we have reduced these prices really with no market pressure essentially, and we have reduced these prices primarily because of the economies of scale. So as the kind of customers, the scale of customers that we have, we have this economies of scale. We can invest more into our infrastructure. We can get more efficiency, and the more we get efficiency, the lower our cost is, and we are happy to pass those costs to our customers. Let me share one more thing actually. Give me 1 second. This is my most recent project. Somebody was asking a question around how do you deploy microservices using Lambda or containers? What should my thought process be? Now, this is something that I've been working on very recently, actually. So you can see the commit history over here. But essentially, what I'm doing is I have a set of 3 microservices here. A web app, which is how you talk to from the client, a greeting app, and a name app. Okay, those 3 microservices essentially. And the goal is to show how to deploy those microservices using. Well, first of all, you build the Docker images from them. So I'm a Java developer, so I have a POM XML. From my POM XML, how do I create Docker images? So I'm showing the Maven integration of the POM images. Then I'm showing how do you use Amazon Fargate, which was a new service that or new technology, not a service, new technology that we introduced at reInvent, where you don't have to manage the container cluster. You just tell us the task definition, and we manage all of that for you. So I'm showing exactly how all of that can be deployed using Amazon Fargate. Same thing with ECS, same thing with Kubernetes, and same thing with Lambda. So essentially, the same set of microservices, how they can be deployed using ECS, Fargate, Kubernetes, and Lambda. And with Lambda, in order to call it an application, for example, we are looking at the concept of AWS Step Functions, because now I can visually orchestrate how my Lambda functions are talking to each other. Similarly, for Kubernetes, if you look at it, we are talking about Helm, Cassonnet, sort of those are the typical application package. We just learned about Kubepack as well, which was announced at Helm Summit about 2 weeks ago. So we're looking at, and then we're also looking at it, how can you create sort of a deployment pipeline with Spinnaker, Jenkins, or how you can monitor your application using X-Ray. So the whole idea over here is, a lot of our customers are trying to set up microservices, and they're asking us guidance, just like you, Lambda or Kubernetes or ECS, what should we do? We're giving them the data points over here, that this is an AWS samples project here essentially. So this is what the GitHub repo is, and this is what I'm evolving. I'm actually going to be back in Paris next month talking about this. There's a 3-hour tutorial planned on this, so I'm giving a deep dive talk on exactly the pros and the cons of it.
Okay, yes, so that was basically my question. It's very good that you're providing all the options, but it would be better if you can also describe, what are the advantages of each approach.
That's the idea. That's what. So if you look at it here, essentially, there's a slides directory over here, and I'm constantly evolving those slides. Now this is going to be a 3-hour tutorial recorded at DevOps France. So April 18th, I think, is the talk. So hopefully a few days after that, the tutorial should be available, and I will tweet it when the tutorial is available. So I know it's a long tutorial, but you can pick the portions that you want to hear. And the order, I haven't decided the order yet, but the way I'm looking at it is, I'll start with Fargate, then talk about ECS, then talk about Kubernetes, and wrap up with Lambda. And I'll talk about, so if on the wiki, for example, if you look at it here, if you go to the wiki, some of the design choices I've started to capture here that, for Lambda, for example, if for some reason your jar is more than 50 MB, you can't do a Lambda function. You have to go Docker container. If you are doing more than 300 seconds, you can't run a Tomcat container over there. Okay, I'm setting a Tomcat container and I'm accepting requests. You can't do that in a Lambda function. So those are your constraints, and more of those we will come up with that as part of this presentation.
You can do it if your calls are stateless, then you don't need them.
Well, actually, as a matter of fact, the way I'm deploying this application is using Wildfly Swarm. And so if my call is stateless, what I do is I run an embedded Wildfly Swarm container, which has a container baked in, and I just get the execution done, but it needs to finish within 300 seconds. So that's an important constraint. Otherwise, the Lambda runtime kills the function.
If you take a company which has a lot of microservices, and let's say that in theory you convert everything to Lambda, how do you handle the understanding of the flow of things, the jungle of code? How do you look at it in terms of one giant repo, all the functions? How do you navigate it?
So I think what you're saying is you're taking one giant ball of mud and converting into small balls of mud. Sorry to put it that way, but I think the important part to understand is, let me show you some tweet. I think you like it.
Moving from microservice management to nanoservice.
Yeah, exactly. So I think this is important consideration. And you look at this, there are about 466 retweets of this, and this all happened within like 3 days. So don't think monolith is a bad thing, or don't think microservices is your golden hammer. You have to have good design principles in the application no matter what. You have to have sort of a domain-driven design. If your application is well designed, so if I, not to boast about it, and my application is very simple actually, as a matter of fact. So if I go here, if I look at my services here, these are 3 simple applications, but at least they're all very clearly named with a master Maven module with multiple sub-modules over there. One of the ways is to actually, if you convert them into all Lambda functions, then AWS Step really gives you a nice way of choreographing them. at least for the runtime aspect of it. And then on the build time of it, you will have to look at it. Are these multi-module Maven files, or what are these? So you're really on the mercy of the language itself, how language allows you to organize such an architecture or such a directory structure, so to say. All right, well, if there are no questions, you can always shoot me a message on Twitter, Arun Gupta. I'm always happy to talk and get more feedback and see what else would you like me to do. Thank you.